I'm going to hit record. Okay, so we just took a look at some ways to do searching. And if you remember back in the previous course, we did this abbreviated version of learning searching, which was linear. And then we went linear and binary. And then we went to sorting. Well, we're going to follow that same idea, just like we did searching more in depth with a binary search tree, with hashing and so forth. We're now going to look at what the basics of sorting were that you learned. And most of you had me for 161, and you should have a program that you did an exchange sort, ta-ta, a selection sort, ta-ta, the Dan sort, which was another version of the exchange sort. And then we did something called a shell sort. Okay, and that did some exchanging as well. Well, hopefully remembering back when we talked about this, you remember we talked about 3 categories of sorts: selection sort, exchange sort, and an insertion sort. And we looked at simple examples for these first 2 to get the concepts down, to get them to work. When we did those, just some notes from it, these sorts will not work well with large sets of data. They're just not good. What do they say? Empirical studies have found, in fact, if I said to you, do you remember the selection sort? What was its big O? O sub what? Little extra for experts.
Sub n.
Yep, close. All right, well, let's see what the selection sort did. See if I can remember how to put this together. In the selection sort, I'm going to start at location 10. All right, so right now I have 10. I'm going to go through and find the smallest number. So I was working with this location. I went through and found the location of the smallest. Oh, 4 smaller than, so right now 10's my smallest, my location is 0. Oh, 4 is smaller, so 4 is my smallest, location is 1. Oh, 2 is my smallest, my location is whatever here. These are size 12. In fact, I kept going all the way out, and I found the smallest to be a 1. Okay, so now I have a little woohoo, I got something exciting happen there. Once I went through the list, I now swapped them. I now made this a 1 and this a 10. And now I moved over to the second number. And I went through and found the smallest. 4 is the smallest, yes. 8, no. 11, no. 6, no. 2, yes. And went all the way out. Once I was done, I went, all right, there's my smallest. I swapped them. This became a 2. This became a 4. And I repeated that process. So I was looking at something where I had an outer loop that went from 0 to 11. I have an inner loop that went from, let's call this counter 1, went from 0 to 11. I have an inner loop that went from something to 12. So when this started at 0, I started at 0 and I looked at 1 all the way out to 11. Yeah, this is subscript 12, or excuse me, subscript 11. So I only need to go 1 to 10, excuse me. So I started at 0 and I looked at 1 to 11. Then I moved over to 1. I looked at 2 to 11. Then I went to 2. I looked at 3 to 11. So my first loop went from 0 to 10. My second loop goes from 1 more than what the first loop currently is. I tracked where the smallest 1 was, and I swapped it with whatever counter 1's location was. Do y'all remember doing a selection sort?
Yes.
Yeah, okay. Most probably, you all have a swap function where we did something along the lines of temp equals A equals B equals temp. Something like that. Okay.
Hmm.
How many times does this loop run? N. How many times does this loop run? N. Worst case scenario, N times N. This is big O of N squared. I hope we're working on our big O notation projects because they are due when?
Next week.
Okay. Oh boy. So selection. I went through and selected and then I swapped. Now the exchange sort. The exchange sort. Does anybody remember how that worked? I
Is that
looked
looking at adjacent things and swapping them if they're out of order?
exactly. So I'm gonna go and check 10 and 4. Do they need swapped?
Yes.
Yes, because I'm gonna put the low. 10 and 8, do they need swapped? The answer is yes.
Yes.
10 and 11, that's good. 11 and 6, they need swapped. 11 and 2, they need swapped. 11 and 9, they need swapped. And if I keep doing this, what's the final result gonna be?
Eventually you'll have a sorted list.
Well, after my first pass through, my largest number will end up at the end. All right, so
Yeah.
what's happening with the exchange sort? I have a while. And while I swap something, that's my outer loop. So I run through this, keeping track. If I swap something, I do it again. If I swap something, I do it again. I have an inner loop that runs from 0 to 11. Okay, side by side exchanges. Here's a loop, here's a loop. What's big O for this guy? He's N squared as well. Let's talk about working with arrays. Yes. Let's talk about working with linked list. Maybe not. Arrays. Sure. Linked list. Remember, the advantage of a linked list was that it was dynamic, and I really don't need to enlarge or reduce my size. Insertion sort. First number is 10. Boom. If I thought of it as an array, I would put 10 in. Second number was 4. Uh-oh. I need to insert it into the right position. So now I would put the 4 in front of the 10. If it goes in front, I have to shift everything after. Now we're thinking about maybe arrays, maybe linked list. Linked list, I don't have to shift everything. So definitely would be better for large sets of data. Next number was 8. I have to put it in between. Here's a 4, here's an 8, here's a 10. So the insertion sort worked basically as I was getting the numbers, I put them in the right spot. Okay, keep that idea in mind as well. As I get numbers, I put them in the right spot. So they're the 3 sorts, 3 basic concept sorts that we have from last year. You remember all of those?
What's the big O notation for the insertion sort?
I'm gonna say N squared because worst case scenario, I have to go through the whole list. And when you say you have to go through the whole list, it defaults to n squared because we're doing it n times for the number of data.
All right, thanks.
Yeah. Okay. Good, 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 good. Now, today we're going to take a look at a better type of selection sort. Same concept as the selection sort, but better than big O sub n squared. And then on Thursday, we're going to look at some other sorts that are going to fit down here, the quick sort, the radix sort, and all of a sudden you're going to be going like, okay, so here's a little bizarreness going on. Now, why are we not doing it until now? Because we're going to use data types that we've recently created to do these deeper kind of sorts, a type of selection sort that works better than O sub n squared. So the heap sort brings in a word everybody just loves. It's heapify. Three types of sorts: selection, exchange, insertion. Good. A heap sort. A heap sort is one that's big O of n log n. Okay. If I said n was 16, for the other ones, it would be 16 times 16 or 256. This one's going to be 16 times what's log base 10 of 16? Let's do a better number. Let n equal 10. The other one was 10 times 10, which is 10 squared. This one is 10 times what is log 10? Anybody? Bueller?
10 log 10 is 10.
That's right. No, 10 log 10 means 10 base 10 of 10. 10 to the what power equals 10?
That's just a 1 then,
That's
right?
just a 1. Yeah, yeah, that's just a 1. So this guy called a heap sort is going to be a much, much faster. Okay, so there's going to be two parts to this. First, we're going to have to build a heap. Once it's built, we're going to do the heap sort. Okay, now why did we not learn about this till now? Because we're going to use a binary tree. Now, you notice it doesn't say binary search tree, because when I set up a binary search tree, I went left or right depending if the number was lower or higher. I set it up for searching. Today, we're going to use a binary tree to help us with sorting. Now, in order for us to sort with this binary tree, first thing is it needs to be complete. Complete was a definition that I gave you some time ago. Which out of these three trees is complete and which one is not? Or are they all complete? Or are none of them complete?
1 and 3.
I hear a 1 and a 3. Since they're exactly the same, and I must have messed up. No, they're complete. They're both complete. Okay, 1 and 3 are both complete. Now, again, get binary search trees out of your mind. Woo, it's gone. Okay, this is a heap. Has the following attributes. It's complete. 1 is complete. 3 is complete. 2 is not, because a complete tree is filled in top from left to right. Boom, 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 boom. Okay. Second rule is the data in each node is greater than or equal to its children. Every node here, is the data in the node greater than or equal to its child?
Yes.
Yes, so this is a heap. Is the data here greater than or equal to all of its children?
Yes.
Yeah, but it wasn't complete, so it's not a heap. Is the data here, every parent greater than its child?
No.
No, because the 8 and the 6 are messed up. So what we're going to learn to do is take a complete binary tree and learn how to turn it into a heap. So by definition, this is a heap. Once I get it to become a heap, I can do a heap sort. Okay, once I get it to become a heap, I'm going to be able to do a heap sort. All right, new data concept. How am I going to do it? Am I going to do it using arrays or linked lists? A quick review of arrays. And by the way, arrays is the one that's going to work the best. A quick review of arrays. When I store a binary tree in an array, where are the children? In the corn. No. Where is n's children?
Left and right.
It's to the left and right. But if I said, I'm giving you the number 4, where's 4's children? Well, I can look at this and go 3, 4, 5, 6, 7, 8, 9, and 10. 4's children are at
Two.
9. Yeah, go ahead.
2n plus 1 and 2n plus 2.
Very good. Just a reminder, we talked about this the other week. It's coming back again. So if I want to find the child, I'm going to go to these locations, 2n plus 1, 2n plus 2. Somebody already came up with the next answer for me. Where are the parents? Well, there is only one parent. If I took the number 11, I need to get 5. If I took the number 12, I need to get 5.
Would be -1 divided by 2 and -2 divided by 2.
Well, there's only going to be one parent. So 11's parent is at 5. 5's
Depends
parent,
on if it's the left or right child.
we came up with a way to find it the other day. We had a formula, a singular formula. Matthew, I think you came up with it.
So it's integer division. So
Yeah,
since it's integer division, I think we can just use n-1 in parentheses divided by 2.
there you go. So 11 becomes 5, 12 becomes 5 as well. We took advantage of that integer division. So far, so good? All right, so we know what a heap is. We know that when we're going to work with it, we're going to work with it with arrays. Feeling kind of good about everything so far. Okay, a heap has some operations. Operations. I need to construct an empty heap. Well, that's just an array. If I start thinking about an array and writing it out, I need to make sure that it's big enough. I need to put in values to make it empty. We're all good with that. Is empty. How would I know if it's empty? What would you do for it to be empty?
Is is the root, if root equals null?
Well, remember, we're not going to use linked lists for this. We're going to use an array.
If index 0 equals null,
Null. Remember, I'm storing integers. Could that be null?
or negative, or just if it's empty, if there's anything there.
What if I said, first of all, I need to be making some notes, array size, and then I might have a variable called count. Every time I add something, I'm going to count it. The next thing is insert. You notice how there is an insert. Okay, I have an insert followed by the term percolate up. Good news is if I have an insert, I don't have a delete because I don't need to delete anything. I need to read these numbers in and then be able to sort them. I need to fill the heap and then be able to sort the heap. Okay. One of the things I'm going to do to get it sorted is retrieve the largest. Now, where will the largest be? In a heap, There's an example right here. Where is the largest number always going to be?
0.
Yeah, it's going to be at the very top here at location 0. So that's not going to be too hard to do at location 0. The next thing is I need to remove the largest number, swap it with something, and percolate down. All right, so let's talk about this. Remove the largest first. So I'm thinking of my heap, okay? And I have it set up. So I'm going to go with this. So 77, 60, 41, 15, 55, and 35. And right now my array looks something like this: 77, 60, 41, 15, 55, and 35. I have location 0, 1, 2, 3, 4, 5, and my array size is 6. Okay. So when I remove the largest, I'm not really getting rid of it. Eventually, this is going to be a sorted array. So where do you think that largest goes? If I had a sorted array here, where would it go?
To the end.
To the end, right? So what I'm going to do is I'm going to put it at the end. Well, where can I put 35? If I'm moving 77 in here, where's 35 have to go?
Swap them.
Yeah, I'm going to have to swap them. Okay, so I'm going to swap them. I'm going to put 35 there and 77. Good. Now, if I think about my heap, I now have 35, 60, 41, 15, 55, and 77. Yay! I know by my array that that's 35, 60, 41, 15, 55, and 77. So in my world of getting it sorted, that's a great thing. Now, my problem is I no longer have a heap. I have something called a semi-heap. And I can fix this by percolating down. 35 is just messing me up. So I'm going to percolate down. Now, I know that to make this a heap again, what number needs to end up here? What's the new largest number in my semi-heap?
Like, what, 60?
60. Yeah. So I'm going to percolate this down. I'm going to move 35 down and swap spots with 60. So I'm swapping it with the greatest one. Oh. In fact, my percolate down is going to continue if I can. 35 is now going to go where? In place 55. So now I have 60, 55, 41, 15, 35, and 77. So now my semi-heap has become a heap again by using percolate down. How did I percolate down? I started at this location, which was 0, and I checked its children using the formulas that we just talked about a moment ago. Checked it, checked it. If it needed swapped, I swapped it and repeated, almost recursive, to check to see again, can I swap it and percolate it down? What's my next step going to be? Well, this one we're no longer looking at. I need to keep track of my last. What's my last? Well, it's 35. So I now take my greatest and I remove the largest. I'm putting 35, just happens to go back up again. Okay. When I swapped it, the 60 came down. And now I have two numbers in the right spot. Right now it's a semi heap. I percolate down. Looks like 35 and 55 are going to switch places. This becomes 55. This is 35. This is 41. This stays 15 because I didn't percolate again. Switch the 55 into 15. 15, 35, 41, 55, woohoo, 60, woohoo, 77, woohoo. After I swap them, I percolate down. Where does the 15 go? Where the
Stays
40 No, because this semi heap isn't a heap. I need to get the largest up here. So
Oh.
15 and 41 are going to get switched. So now I have 41, 35, and 15 left. Because my other numbers are like solid. I switch 40, yeah. So the 15 ends up going back up. And eventually I should end up with my sorted array by doing this percolating down. Questions? Should we make up another dummy set of data and see if you go through the right steps? Do I need to put the poll up? Change the word from
I say we
hashtag.
do it again.
Do it again. Give me some numbers.
1,
Yeah,
15,
keep going,
30,
keep going. 8,
100,
100, 16, 2.
42.
Let's go with just those numbers, all right? So now I'm working with just the array. And I'm gonna say, okay, I want to, is it complete? Is it a heap? Yeah, I don't have any of that going. When I was over here, I had a heap to start. Okay, so I don't really have a heap to start with these numbers. So one of the things we're gonna have to do in a little bit is come back to these numbers and figure out how to build a heap. So instead of starting with that, let's start with something that's actually gonna work. And let's start with 66. Don't throw those numbers away. We'll come back to that. 66, 41, 12, 5, 2, 11, and 9. Is that a heap?
Yeah.
Yes. So we're right now again practicing removing the largest. So go ahead and draw a couple of graphs all the way down, and then we'll see if we end up with the same, well, we should end up with the same final graph. All right, so I swapped 66 and 9. Put 66 in the right spot, put 9 up. Percolate down. 9 and 41 get exchanged. That's as far as 9 has to go. I now switch my largest with the last, which moves 41 down, which puts 11 up. I percolate down. 12 and 11 switch. I now take the largest and put it in the last spot. So I take 12, move it to the bottom, move 2 to the top. I percolate down. It swaps with the 11. I now take the largest, put it at the end. It's here. 5 is left. 5, 9, and 2. I percolate down. It puts the 9 up. I now take the largest and swap it with the end. You know, I keep doing largest, swapping it with the end. 9 goes down, goes to the end. I'm left with 2 and 5. I percolate down. I'm left with 5 and 2. I swap to move the 5 to the last spot. The 2 should be in the first spot. CJ, you got it? He says yes. All right, so let's go back to our dilemma here. And our dilemma is, what if I have a list of numbers and they're not in a heap? I need to make them a heap. And how do I go about doing it? Well, we're going to look at 2 ways. Okay. The first way is I'm going to take a look at this bad boy, and I'm going to say, I'm going to add to the end and percolate up. All right. So I put in 1. 1 is 1. I put in 15. So in my world of completeness, I put in the 15 and I'm going to percolate up, because if I percolate up, it's going to move the highest up. I put in 30 and I percolate up. So there was my first one. Here's my second one. Here's my third one. You know, I put that in and I percolate up. Now I have 31 and 15. My next number is 8. I have 30, 1, 8, and 15. And 8 percolates up. Now I have 30, I have 8, I have 1, and I have 15. I swapped these 2. Okay, I swapped those 2. I swapped those 2. My next number I'm going to add is 100. It percolates up and it percolates up again. So when I percolate up, the 100 is now going to go here. The 30 is going to go there. The 8 is going to go down there. Okay. Next number is 16. It's only going to go up once. So now I have 100. I have 30. I have 15. I have 1. I have 8. Whoop, excuse me, that's 16. Now I have 15. My last number I put in is 2. I now have a heap. Let's see, I added to the end, percolate up. So if I had 2, 4, 6, 7 numbers, I had to percolate up 7 times. But in turn, I ended up with my heap. Boom, 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 boom. And now I'm ready to do the heap sort to put it in a sorted order. So I build the heap first. Do the sort of, how am I doing the, well, I put the 1 in, and then when I put 15 in, I check with its parent. And if it has another parent, I keep doing it. I put the 30 in and checked with its parent, seeing if I had to swap. I put the 8 in, I had to check with its parent. If I made a swap, I would have had to check it again with the upper parent. So if this would have been greater than 30, I would have had to check again. So I keep percolating up by looking at the parents in the array. Not sure how I would do this with linked list. So the first option to inserting items is what you see above. Add the item to the end, percolate up. The second option is going to be a little bit different, a little more efficient. I'm going to take this the way it is to start. 1, 15, 30, 8, 100, 16, and 2. Now up here I did percolate up 7 times. Not the best. This time I'm going to percolate down. Now, what numbers might be out of order when I try to percolate down? Well, there's only going to be 3. That's this one, and this one. So I'm only looking at parents to see if they percolate down. And I'm going to start with the lowest down here parent. Lowest down here parent. So I'm going to start at 30. Let's see. Would I be able to come up with a formula to find out where my first parent is? Yeah, I mean, lots of math coming into play. If it's, you know, how many numbers I have, we'd have to sit here and look at side-by-side comparisons. You know, here's 7 numbers. The first parent is at 3. You know, if I had 10 numbers, where's the first parent, and so on, till we came up with a formula to be able to detect where's my first parent, and from where that parent is, I want to percolate down. All right, so if I take a look at 30, can I percolate it down? What's the answer? No. Good. So now I'm going to stay with that. I now have the same one. 8, 100, 16, and 2. This time I'm going to move over to the left in my array. 15. Do I need to percolate it down? So this time I'm starting at 15. I'm going, yeah, I'm going to percolate it down. I'm going to go to there. So now I have 1, 100, 30, 8, 15, 16, and 2. The last number I have to check is my top number. Can I percolate it down? Yep, it switches with the 100. Now this is a 1, and it's going to switch with the 15. Now that's a 1. So again, I'm looking at, when I percolate down, finding my 2 children, which one is the largest, move to that. Then I find out if it's smaller than my children. If it is, I swap it with the largest. And just like that, in a matter of not 7, but 3 perk downs, I build a heap. Once my heap is built, I'm ready to sort it. Do the heap sort, switch 102. Once I have 2, you know, then I needed to percolate it down, just like we did with that other list. So when I'm inserting items, I have 2 choices. One, I can put the numbers in one at a time. Put in 1. My second number is 15. I'm going, oh yeah, I had to swap 15 and 1. My next number was 30. I checked 30 with its parent. The next number was 8. I checked 8 with its parent. If I made the swap, I checked with the parent up above, kind of deal. The idea of percolating up. The idea of percolating down. Give us another example. I will. I'm feeling very perky today. Sorry. Which method do you think was easier? The first one? With,
Second.
yeah, with just the percolate downs instead of the percolate up. Let's do 8, 4, 11, 6, 1, 21, 22, 2, 3. All right. We should all, and let's do method 2, where I already have my array filled, but in my head, I'm thinking of this as a binary tree. Okay, I'm thinking of it as a binary tree. It's already filled, and I want to make it a heap by percolating up, starting at the first parent. Woo, I think I said that right. How many times will I be looking to percolate down? How many parents are there?
What, 4?
4. Yep. 6, 11, 4, and 8. Mark, did you ever show up? Somebody left. Oh, they had enough of this. Starting at the 6. I don't have to percolate down. Nice. The 11, I do have to percolate down. 8, 4, 22. That became 11. My next location is here. You know, and I could be tracking all this. 1, 0, 1, 2, 3. I checked location 3. I checked the location 2. I'm now checking location 1. I'm percolating down. It's going to switch with the 6. And it looks like that's about it. 8, 6, 22. There's the 4, the 1, 2, 3, 21, 11. Now I'm checking my last location, which is location 0. Looks like I'm going to move it where? 8's going to end up in what spot? Is it smaller than the largest child? Yes. So it's going to go here. Is it small? Yeah. So this is going to become 22. This is going to become 8. This is going to become 21. That's going to become 8. 22, 6, 21. 4, 1, 2, 3, 8, and 11. I got my heap. Two, 4, 6, 8 numbers. I had 4 perks. Questions? Ken, you tell me if you had a question, wouldn't you?
My what?
if you had questions. What do we have here? The shell sort named for Donald Shell. Okay, so why is he wasting time telling us this? On the final exam, I'm going to have things like what somebody did and what their last name is, or what their name is. So, for example, Donald Shell could be a question. Who's known for doing the heap sort? Somebody take a guess, see if you know it.
The guy who composed Star Wars.
Yes, exactly. That was an excellent answer, John Williams. Okay, so again, this is in the NIOF book. It's not what's in the Gaddis book. And if you wanted to really delve into it, there's an algorithm for percolate down. Hopefully you would be able to follow it a little bit. There's an algorithm over here for percolate up. Okay, there's the heap sort. And finally, here's the Heapify algorithm. Converts a binary tree into a heap. And that's what we were doing. We were turning a binary tree into a heap. We did it two different ways. Okay, it's the inserting of the numbers. Heapify, percolate down. Questions?
So our
Somebody-
project due on Friday, I'm assuming you want max heap.
The assignment that's due on Friday. What is the assignment due on Friday?
The Heaps project.
Let me stop this for a second.